Okay, so we're back at looking at different ways to measure how bad somebody's oxygenation is. And we looked at when somebody has a difficulty with oxygenating, we call it a VQ mismatch. When it becomes severe, then it's referred to as a shunt. But even though you are measuring, a VQ mismatch would just be a small shunt is all, really. But it also, VQ mismatch is also dead space. So that's, you just want to wrap around that, okay? Now we also have the AA gradient. So we know that when we give somebody oxygen, we expect it to go into the arterial PO2, but that doesn't always happen. And in fact, it naturally doesn't happen because we have a normal AA gradient of, maybe 5 to 10, and then as it goes up to 100%, it could be 65. Now, as a rule of thumb, remember the AA gradient is approximately the FiO2. So you can approximately have that much AaO2 gradient and still be considered normal because these numbers here are more precise, but you have enough numbers to remember. So if you can just remember that normally it should be about the FiO2, you'll be okay. And look at the AA gradient on 100% of greater than 300, and that would be severe shunting, absolutely. We also have the AA ratio. So here's another way that they could give you an example of somebody who is hypoxemic. And again, if they start to do this to you and you're like, what? Then calculate it out with normal numbers, okay? And so normally you should have a number that's greater than 0.75. When it gets low like this, then you definitely have hypoxemia due to shunting, what would be considered the level for shunting, and then this level for disease or VQ mismatch. And then here is our oxygenation index, and if you remember that one, that's FiO2 times the mean airway pressure times 100 divided by the PaO2, and this is used to transfer those infants to where they can receive high frequency oscillation and possibly ECMO if it gets to greater than 40. So there are some numbers that you want to think about here. 20, they're going to have to start looking at alternative forms of ventilation, the oscillator, and at 40, then they need to consider ECMO. All right, so let's look at this content formula so that we can calculate the shunt. We know that the shunt involves this content formula. So O2 is transported in the body two ways. It's bound to hemoglobin and dissolved. The majority is bound to hemoglobin with only 0.3% that's dissolved, but we have to take it both into consideration, and the formula does that. So we have, this is the part that's bound to the hemoglobin. So we're going to take the hemoglobin times the amount of oxygen that it can hold, and that's 1.34 per 100 mLs, and times the saturation of the hemoglobin. Add in that to the P, I should have put little a, O2, times 0.003, and the normal arterial content is in the high teens. So we're somewhere around 17 to 20. It's going to be in the high teens. And then you have to also remember that when you're calculating the shunt equation, you have the venous blood to consider, and you want to make sure you utilize the right numbers, and you use the venous numbers for calculating the venous part. And we're also going to look at the end capillary blood, or that CC prime O2. So let's take a look at how this formula would play out. If we had a hemoglobin of 14 with a saturation of 96% and a PaO2 of 90, then we would take that hemoglobin of 14 times our 1.34 times the saturation, which is 96%, and then add that to 0.003. So we took our 3%, our 0.3%, and we turned it into a decimal. That's how we got the 0.003 times 90. So that's 18 plus 0.27, and then we add those two together and we get 18.27 volumes percent. Content is always delivered in volumes percent is the units. So, and this is our high teens. So this is normal. Are these numbers normal? Yeah, they look fine. So we know that women can have hemoglobins as low as 12, even though we learned that 15 is pretty much, the number we like to use. And 96 is a fine SAT, and 90 is a fine PO2. And so did we get in the high teens? We did. So you also want to always go back and make sure that your numbers make sense to you. Now, here is the classic physiologic shunt equation. Dun, dun, dun. So it is the C prime O2 minus the C little a O2 divided by the C prime O2 minus the CV O2. So the C prime, again, it represents the content of oxygen that's present in the capillaries at the alveolar capillary membrane. It represents a perfect diffusion of oxygen from the alveoli to the capillary. But we know that perfect doesn't exist, and we're getting ready to calculate that right now. But also, we can't measure the exact blood that's in that capillary. We can't take a sample. So we have no way to sample the capillary blood. So we must just take what we know, which is the alveolar air, and that's what we're going to use. We're going to have to use the alveolar air equation. So, because we know how much oxygen the patient is on, and we know his CO2. And so we have to, we're going to assume a perfect transference of that gas at the alveolar capillary level. And here we go. Here's our CC prime. If the FiO2 is 50% and the hemoglobin is 15, then the grams percent, I forgot my little gram, I'm sorry. The P little a CO2 is 40. Then what is the CC prime? So here's our CC prime, again, back to our original equation, hemoglobin times 1.34 times the SAT, which we're always going to use as 100%. We're always going to assume that 100% of it is saturated. And then we're going to add that to the P big AO2 times 0.003. So the big A is what? Alveolar. The alveolar O2. So that means we need our alveolar air equation. So let's try it. We always assume 760 unless otherwise stated. We're on 50%. We have a CO2 of 40. We have a hemoglobin of 15. We have a PaO2 of 70. And we have a SAT of 93. And here's some extra numbers that we're going to need later. We have a PVO2 of 38 and a PVO2 of 65. So first thing we have to calculate is the alveolar air equation. So here it is. The P big AO2 is equal to 760 minus 47 times the FiO2 of 0.5 minus the CO2 times 1.25 or divided by 0.8. So y'all remember that one, right? If they don't give you if they don't give you the barometric pressure, you're just going to assume 760. If they don't give you the water vapor pressure, you're going to do it to normal body temperature, and you're going to use 47. So here we have 356.5 minus 50 equals 306.5. Now that's going to go into our content formula. So let's look at it. CC prime O2 is equal to hemoglobin times 1.34 times the SAT plus the P big AO2 times 0.003. So C prime O2 would be now equal to 15 times 1.34 times 1.0. And then we're going to add to that what we got from our alveolar air equation, because that's our P big AO2, is 306.5 times 0.003. So our C prime would then be 20.1 plus 0.92, which equals 21.02 volumes percent. So now we're halfway done. We just have to find out what the C little AO2 is and what the C VO2 is, okay? So on the next one, we see that the calculation for CaO2 gives us 15 times 1.34 times 0.93. Where did I get the 0.93? That was given. The SAT of the oxygen was 93%. Plus, what is his P little AO2? Because now we're doing the content of arterial oxygen. So his P little AO2, we look up here and try to find it. And there it is, the P little AO2, that should have been a little a, I'm so sorry, is 70. And so we plug that in. Sometimes when you do these things, they turn things into caps that you don't want. And that's times the dissolved of 0.003. So now we have 18.69 plus 0.21 is equal to 18.9 volumes percent. And then we're going to do the same thing for the venous side, but we've got to find the venous numbers. So we're going to look up here. We need the venous SAT. There it is, 65. We need the venous PO2, the PVO2. And we'll look up here and find the PVO2. There it is, 38. And then this is the dissolved number. So we have 15 times 1.34 is times 0.65 is 13.07 plus 38 times 0.003, which was 0.11, and that equals 13.18 volumes percent. Now we can plug in our number from the other side. So we have, there's our 21.02 minus 18.9 divided by 2102 minus 13.18, you get 2.12 divided by 7.84, and that comes out to 0.27 or 27%. So what category would that fall in? If you said moderate shunt, then you're correct.